All right, in this video, I'm going to be talking about some examples of the law of conservation of energy. So the law of conservation of energy is basically, we've already talked about that, is the initial energy plus any work done by any external forces equals the total energy later. Now, the work done by external forces all depends on how you choose your system, right? And I think we spent enough time talking about this system business, right? So the first example I'm going to do is that I'm going to have something going down a ramp, right? Okay, starting with some velocity, not even starting from rest, it has some initial velocity here, and I want to find its velocity when it's at the bottom of the ramp, and then I'll add to this. So, and let's just say that there is some friction here. Okay, so my equation should be written as the initial. If I choose this level here as 0 for gravitational potential energy, then I have kinetic energy up here, so which is 1/2 mv initial square. Let's just say this height here is h plus mgh, assuming this object has a mass m. Okay, and there is some work done by friction, so plus the work done by friction. Okay, in between the top and the bottom, and that should equal to the amount of energy, total energy that I have at the bottom. Well, at the bottom, the only thing I really have is just 1/2 mv squared, just kinetic energy. So the v here is the v of the ball when it's at the very bottom of that ramp. And I can do this anywhere in between, right? So for instance, if I'm at this point here, let's just call this point P, right? When I'm there, I'm just going to have 1/2 mv0 square plus mgh, which is a different h, just this much, okay? Plus, you still have some kinetic energy here, right? Plus the work done by friction, but only for this part of the ramp, okay? And that should equal, it's 1/2 mv square plus mg, this height, right? Plus the work done by friction in between equals the kinetic energy and the potential energy here. That's what it should be. Okay. Now let's say this object, let's just say it's a block sliding, and it comes down here to this surface, and there is a spring waiting for it. Okay. And it's going to hit the spring, it's going to compress it. So I want to know what's the relationship between the energy that's coming in the block and the compression of the spring. So when I'm at this level here, let's just say there is a different mu here, call it mu2, right? When I'm here, well, I have the kinetic energy of that block is basically whatever this is, okay? Okay, plus the work done by friction in this part, because the coefficient of friction is different surfaces, okay? And there is nothing else. And that should equal, let's just say, this compresses all the way, right? So it stops, the block stops moving, the spring is compressed all the way, so all that energy is now sitting in the spring. And then the rest is really just plugging numbers in. So you should pretty much know how to do the numbers if you have to, okay? All right. All right, the next example will be a pendulum, right? So I have a pendulum, then I'm going to raise it to a certain height, and I'm going to try to do the work energy theorem to figure out maybe the speed down here, or to what height do I have to raise it to, or I have a certain speed. So let's just say this angle here is theta, right? And the length of the pendulum is L. So both of this, I know it doesn't look like they are equal, but this is the length of the pendulum. It's the same pendulum on the other side. And I'm going to try to, let's say, find the speed. So it's going in this direction. When it's down here, it's going in this direction. It's horizontal. I'm going to try to write an equation that will help me find the speed at that point, at the lowest point. So that's going to be the maximum speed, because that's going to be the lowest amount of gravitational potential energy you're going to have. Now I'm going to choose the lowest point as the 0 for gravitational potential energy. And again, you can choose whatever you want. It's up to you. But I'm going to choose the lowest point all the time. So it just makes the math simple. I never have to deal with this concept of negative potential energy. Okay. So now, when I'm up here, position 1 or I and F here, this is the height that I'm concerned with. Right? So it's going to be 1/2, not 1/2, mgh. Okay. Then when I'm all the way down here, all my gravitational potential energy is converted to kinetic energy. That's going to be 1/2 mv squared. Right? Now the question is, how do I find h? Well, I'm not going to actually tell you, I'm not going to show you, but I'll give you a hint. Okay? So that height, instead of looking at it here, try to look at it in here. Right? Okay? And keep in mind that this whole thing here is L, right? And you're trying to figure this out. So I think if you can somehow figure out what this distance is, maybe inside this triangle, right? You can figure out what h is. Now, I'll give you the formula for h, and you have to kind of like prove it yourself. It's L minus L cosine of that angle up there. Okay? All right. So now you can see that as the bob is falling down here, right, is swinging, you lose your gravitational potential energy because you're closer to the reference. And whatever you lose as gravitational potential energy turns it into kinetic energy. So the bottom line is your total energy stays the same. Your overall mechanical energy stays the same if there is no friction. Okay. The next example we're going to do is we're going to do something on a roller coaster, right? So, and I'm going to do this without friction. Okay. So let's say we start up here with some speed. You're not starting from rest. Okay. And this object here slides down and it comes around. And let's just say this shape here, this loop, is a circle. Okay. And I'm going to try to find the, what we call the g-force at these two places, and I'll explain that in a minute. All right, so I'm going to try to do the, let's just say this has a radius r. This height here is h. I'm going to pick the lowest point as the reference for gravitational potential energy. So let's write our equations. At the very top here, I have mgh for gravitational potential energy, and I'm going to assume that this whole surface is frictionless, plus 1/2 m v0 squared. Now, there is no external work done by anything because I'm going to pick the Earth as part of my system, and I'm going to say that there is no friction here. So there is no external agents doing any work on the system. Okay, and I'm going to try to find maybe my speed at the lowest point here. Okay, so that's going to be 1/2 mv at the bottom square. I'll just call it b for bottom. Right? So you see how the mass doesn't really matter. Now I'm going to try to find out what that vb is. And I think we should throw some numbers in here. So let's just say this is 10 meters per second, okay? And I'm going to give this mass here 2 kilograms, which is not important for us now, but it will come in handy later. So VB is basically G, which is 10 times, I have to give this height maybe like, I don't know, let's just say 20 meters, right? So 10 times 20 plus half times 10 squared. Okay, plus, well, this is half of VB squared, plus, that's it. Okay, so now this is going to be 200 plus, what is that, 50? So we multiply all of that by 2, so this is going to be 500. So VB is going to be square root of 500, and you can put that in your calculator and come up with the number in meters per second. All right. So let's say the radius of this is, I'm going to say, I'll pick 4 meters. Okay. Now I want to figure out how fast I'm going at the top. Same concept, right? The only difference is that at the top here, I do have some gravitational potential energy. So let's try that. So I'm going to start, I can do this 2 ways actually. I can consider this lowest point as my initial position, initial condition now, and then I look at the top here as my final, right? Or I can just start from the top here. It doesn't really matter. Keep in mind that the sum of the energies throughout this whole path stays the same. So it doesn't matter how you do it. So let's do it here. So I'm going to say 1/2 mv0 squared plus mg times h. That should equal the gravitational potential energy here, which is mg times 8. The radius is 4, so you're like 8 meters above the ground, or above this reference, plus 1/2 mv, I guess, at the top square. Okay, so what do we have here? So we take out the masses. Okay, I think we can take out the halves and multiply these guys by 2. You can do whatever you want to do when it comes to the algebra at this point. So V T equals, all right, that's going to be, that's 100 plus, what is that, 20 times 20, that's 400, minus this amount here, which is 16, so 160. Yeah, so with a radical, of course. So VT equals, so is the 500, so this is 340, it looks like. Yeah, so this gives me a negative 60, yeah, 340. So radical 340 in meters per second. Now I want to find the g-force. Now the definition of g-force is basically your normal force over your weight, right? Okay, g-force. And that's basically the feeling that you're getting, how much heavier or how much lighter you're feeling when you are on this roller coaster. So let's try that. So let me see, I have to keep some things here. So I'm going to keep the V at the bottom is radical 500, and the V at the top is radical 340. Okay. So now when I'm at the bottom, I'm going to go back to the centripetal force stuff. I have the normal force going up, and I have the mg acting down. So I should write Fn minus mg is mv squared over r. So which makes Fn mv squared over r plus mg. And that's going to be 2 times, now the v at the bottom is radical 500, so when you square that, you just get 500. Radius is 4 plus, so I factor out the 2 already for the mass, plus 10. So this is 125 plus, so 135 times 2 is 270. Let me just try on the calculator. 125, 135. Yeah, it looks right. Yeah. Yep. Okay. Now I'm going to do it at the very top. At the very top, you have Fn plus mg equals mv at the top square over the radius. Okay. So Fn is m. Now I'm going to take out the, I'm going to factor out the mass, which is a 2. V at the top square, that's 340 over 4 minus 10. Okay, so Fn becomes, so let me just put that in the calculator. 340 divided by 4 minus 10. The whole thing times 2. So I get 150. 150 newtons, right? Now, the G force at the bottom, okay, down here, G force will be 270 over 20, right? So that's about 13 and a half. No units, because you're doing the ratio of two forces. Okay. The G force at the top would be 150 over 20, which is 7.5. Okay. Now, if this loop here is a circle, you can prove, and which we're not going to do. The difference in the G forces is always a 6, no matter what the speeds are, right? And you can prove that. It's not a super hard proof, but you can do it. So this is 13.5, this is 7.5. A difference between them is always going to be 6, only if it's a circle. If it's a different shape, like we'll do in class, it's going to be different, right? All right, the next example, I'm going to talk about this concept of escape velocity, meaning like at what velocity should we fire a projectile or a rocket so that we'll never see it again. It just disappears. It's gone into space. All right. Now, as you go higher above the surface of the Earth, the acceleration of gravity is no longer constant. So gravitational potential energy is no longer just mgh, because the g changes. Now I'm going to give you a formula, okay? But I won't be able to prove it to you until you guys take calculus. So you have to take calculus in order to do this. There's something called integrals, or if you do physics C, you'll see how it works. So negative g, the mass of the two objects, divided by the distance between them. Okay. Now, this is gravitational potential energy. This is true when the acceleration of gravity is no longer constant, because you know that it changes as follows the inverse square law. Now, this is what we're going to do. We're going to pick infinity, right, as our reference for gravitational potential energy. Okay, and we're going to pick the surface of the Earth. Okay, and we're going to try to do the conservation of energy between the surface of the Earth and infinity, right? So think about it this way. Just infinity is like if you throw something up, right? It gets to the highest point, and it stops and it turns around, right? Well, think about it like the rocket will reach infinity before it stops. Well, the problem is that you can never reach infinity, right? So let's see how we can do this. So down here, my gravitational potential energy follows that rule there. Negative g, the mass of my satellite times the mass of Earth over. Now, if I'm sitting at the surface, right, the distance is the radius of the Earth. Now, when I fire that rocket, I do have some kinetic energy. This is the mass of the satellite, or rocket, or whatever. Rocket, I guess. Okay. Now let's see what kind of energy do I have at the end, at infinity. Well, I set my gravitational potential energy. I set the reference for gravitational potential energy to be 0 at infinity. So I have no gravitational potential energy. Now, the kinetic energy, think of it like I throw this up, and when it reaches a certain point, the kinetic energy is 0, right? Well, I have to do this all the way at infinity. So my kinetic energy will be 0 somewhere, right? But the problem is that you can never reach infinity. So now this is what we call the escape velocity. If you fire it with this speed, and if you can respect this equation, you will never see it again. So let's see how this works. Okay, I can take care of this, the mass of the rocket. The V, escape, is going to be equal to, so now I got to move this to the other side, the negative will go away, so it should look something like this, 2g m e over r with the radical. Now that's something you can come up with yourself. If you just have to manipulate that equation a little bit, right? And that should do it.
All right, I'm out. Peace.